Hello, everyone. I just want to say good evening to everyone. My name is Maggie Ray, and I will be co hosting with our presenter. Thank you for joining us this evening for the Beginning Gardener series. Tonight's presentation will be on soils. Just a few reminders during the program, please stay muted the whole time and do not share video. If you have any questions for the presenter during the program, please type them into the chat box and I will ask them at the end of the program. If you have any technical questions or problems with your viewing of the program, please refer those to the chat box as well, or you can email me. And all that information, including my email, is located in the chat box. As usual, this program will be recorded and it will be emailed to you as soon as it's made available to us. Our presenter today is Austin Little. Austin is a University of Illinois Extension horticulture educator from Southern Illinois. He covers Jackson, Franklin, Williamson, Randolph, and Perry counties. With that, I will go ahead and let Austin take it away.
Okay, thanks, Maggie. Thank you for the introduction. And hello to everybody, and welcome you this evening to this installment of the Beginner Gardener series. And our topic tonight is soils. So I'm originally from Adams County, where we claim to have the best soil in the world. And so that's where I first became interested. That's where I got into soils. Let me pull up the PowerPoint here. And so tonight, what we'll be talking about is, technical difficulties here. Okay, so tonight we'll be talking about soil physical and chemical properties, some common issues that gardeners run into with soil, and how to improve our soil in the context of home gardening. And so soil is not dirt. So dirt is the accumulation, is the stuff that we clean off of our cars or what we sweep up off of the kitchen floor. The more complete definition of soil is the unconsolidated mineral or organic material on the immediate surface of the earth that serves as a natural medium for the growth of land plants. And to be more specific, soil is comprised of minerals, particles, organic matter, living things, gas, and liquids. So soil is mainly comprised of mineral material. That's the primary component. That's about around half, a little less than half, is comprised of minerals. And in an ideal situation, we have 25% water, 25% gas or air porosity, and around 5% organic matter. Now that would be an ideal soil composition. And this is a good balance of pore space and water holding space, oxygen, pores for oxygen to move around in, which is necessary for a healthy soil function. And then there's the other component there, which is, I guess you could say, is part of the organic matter, but there's the living biotic component, and that's around 1% of soil composition, and that's including bacteria, soil organisms, fungi, all of these organisms that contribute to the soil food web. And here we're going to take a look at an example of a not so ideal soil. So this would be a compacted soil or a degraded soil, like a heavy clay kind of soil that we often, it seems like that's the majority of the soils that we find in our home landscapes quite often. And in this case, we have a higher content of minerals, and clay minerals specifically. Maybe we're still going to have that organic matter, but we have a lot less water capacity and about the same air capacity. And this is a look, okay, so if we're kind of visualizing soil structure, soil is comprised of three main sizes of mineral particles, and this is sand, silt, and clay. So to kind of better visualize the differences in the sizes of these particles, we can think of a basketball. So if we're thinking of the size of a grain of sand as a basketball compared to the silt and sand particles, a silt particle would be the size of a ping pong ball or a bouncy ball, a rubber bouncy ball. And the clay particle would be the size of a pea in relative to the particle size of a basketball. So that's a good way to kind of understand the differences in the sizes of these soil particles in the mineral portion. And what we're looking at here is the soil texture triangle. And this is the classic diagram texture triangle that every intro to soil student has seen in the first in the first lesson or two of Soil Science 101. And it's a really useful tool because it helps to show us the different percentages of soil particles that contribute to a soil texture profile. And so looking at this triangle, at the texture triangle, if we're looking at a silt or a silty clay loam, that is going to be right about here. And if we're kind of looking at these arrows, these tell us some useful information. So on the percent silt side, we're looking at where these lines intersect. Going this way from percent clay, we're going to move over from left to right, and from the sand down here, we're going to move up from the bottom in a diagonal. So what this is telling us is if I move down to here, I can see that we have 20% sand. Looking up here, we have 50% silt. So that gets us to 70%, and we have 30% clay. So that's kind of right on the edge of a silty clay loam. And in each of these regions, it tells us generally what texture of soil we'll be looking at. And if we're looking over at a sandy clay loam, let's just say, oops, let me back up. Let's just say that we're looking kind of right here. This would tell us that we have 30% sand, 60% sand, 30% clay, and 10% silt. And that would be a sandy clay loam. And all of these are pretty desirable textures. A loam is going to be the more desirable soil texture. So if you've ever heard of a loamy soil, that's a soil that's generally well draining, has good nutrient and water holding capacity, which are these qualities that are more desirable in a soil because they're better for growing plants and better for biological activity. Whereas we get into more of a clay or sticky, silty soil, we begin to have issues with drainage, water holding capacity, and things such as this. So that is the soil texture triangle. And to kind of take a closer look at what's happening here within the pore spaces between the particles. Depending on the composition of texture, a soil will have more or less macro and or micropores. So this is the interface, or kind of the stage where we get the exchange of nutrients, air, water, and biological activity. So this is kind of where all the chemistry and physical activity exchange is happening in these macropores between PEDs. And PEDs are the kind of the smaller aggregates of soil particles which form the larger soil structures of clods and even larger soil fragments. But really the main point here is this is kind of smaller soil aggregates where macropores are created. And macropores are responsible for drainage, air movement. This is where the majority of soil organisms move around and where root channels are created. And then within PEDs, we have micropores. And so we kind of see an electron scanning microscope image here of micropores. And micropores, the water held within micropores can only be accessed through suction, so or capillary rise. So it has to be moved physically out of there by some outside force besides gravity. And the micropores are also responsible for how soil filters and detoxifies pollutants out of water. And those are the kind of primary functions of macro and micropores. And here we have a closer look at soil. So this is kind of an illustration of what could be a PED, or a soil aggregate here. So these larger pieces here are going to be the sand, and that again kind of relating that to the smaller pieces. And this might not be quite the scale, but it just kind of illustrates the composition here. So here we have clay particles, organic matter, our air pockets, H2O, and our bacteria here, our biological component or biotic component. And so these clay particles, this will be of some importance a little bit later, but clay particles are made up primarily of silica, aluminum, and magnesium. And these are negatively charged, kind of layered particles. And that has a lot to do with some other soil physical and chemical properties that we'll talk about. So how does soil form? Where does it arise from? The main primary source of soil is derived from parent materials. And parent materials generally are originally from bedrock, but that material is often deposited in a multitude of ways and moved around the surface of the earth. So one of the primary ways is through wind. A good example of that is through wind erosion, which is something we try to control and try to mitigate. But in the natural course of creation of soil, that is one common action of creating soil, and that's known as loess or less soil. Another very common and very active form of soil creation is through the movement of water. So water moving over bedrock surfaces is a form of weathering, and those deposits are called alluvium deposits. And another major process going on simultaneously here. So these processes happen simultaneously. They don't happen separately in isolation. And Another process is the biotic process, the activity of organisms on soil, breaking things down, digesting, processing, and conditioning soils. So as the biotic the biotic component of soil, as it digests soil organic matter, it releases chemicals and compounds that chemically break down bedrock as well. Weathering over time, so fluctuations of warm weather, hot temperatures, freezing temperatures. This causes freezing and thawing and physical breakdown that way through ice formation, expansion, and breaking apart parent material over time. And so all of these simultaneously are acting to create soils. And in our region, in especially Illinois, one of the primary processes, historical processes of forming our soils was through glacial activity. And as glaciers formed and receded over hundreds of thousands of years, they deposit massive amounts of parent material through what's called glacial till and outwash when the glaciers recede away eventually. And you can see here, our diagram shows the first major ice age that we have in record that's relevant to Illinois. Before, this was mostly covered in ocean, but in the context of our current geology, the first one here was more widespread. Second one kind of didn't quite go quite as far west, and then the third one was a little bit further north. And here in southern Illinois, that has a lot to do with why our geology and our soils are a bit different than further north. So we have some more, one of the issues in southern Illinois is that almost everybody runs into clay and silt soils, and that's because those finer particles are what ends up washing out in the moraines. So southern Illinois was a large moraine down here where the coarser things ended up further up north, and we ended up with the till and the moraines in our area. And all of those processes, those soil forming processes, contribute to eventually, over time, a soil profile. A soil profile doesn't arise, over hundreds of years. This takes hundreds of thousands, if not millions of years to develop. And the ideal soil profile has 10 to 12 inches of rich, dark topsoil, and that's going to be where the vast majority of the biological activity is happening, where we're having the interactions between roots and the biotic component of soil. That's where all of the mycorrhiza is active, all of the bacteria, all of the nutrient cycling, all of that fun stuff is going on primarily in the top 12 inches. And of course, we do have root penetration deeper than that, especially with native plants. They can go very much deeper, which is good because it helps to condition soil, open soil up, and bring up otherwise unavailable nutrients and resources from the lower profile. But in the context of the beginning home gardener, what we're really focusing on is mostly the A and B horizons. And the top A horizon is our topsoil, the B horizon is our subsoil, and then that C horizon is called the substratum, parent material, or bedrock. And kind of a little bit more description here on soil forming factors and parent material as it pertains to glacial activity. So here we see the outwash plain. So this is all after a glacier has receded. And we see the outwash plain here. So this is formed from glacial sediments that are deposited by meltwater and outwash at the edge of a receding glacier. Whereas the till is the sediment. So this is kind of this front edge of a glacier as it's pushing this material, as it's forming, as it's moving along, and then that would basically stop where the glacier stops and starts to recede back. And here we have the ground moraine. So the ground moraine is, as we mentioned, southern Illinois, these rolling hills. That has a lot to do with glacial activity, and this is where where the lighter clay and silt material is deposited out into these ground moraines or plains. So now we're going to transition here to talking a little bit more about organic matter and soil chemistry. So soil organic matter, as we saw, is a small but essential, critical part of a healthy soil. If you don't have organic matter, you don't have the bacterial, the biotic component, and you have what could be called a sterile or inactive or soil that's not really alive. So this living component of soil is a very important part for it to provide us the services that we're looking for. So soil organic matter is formed from the once living the once living parts of living material that is broken down by the living component of soil, the soil organisms, and that's bacteria, fungi, earthworms, amoebas, nematodes, all of these other microbial activity. And soil organisms utilize this organic matter as a food source. And as it's digested, these microorganisms exude nutrients and materials that turn into humus. And ideally, a garden soil or a landscaping kind of soil is going to have between 4 and 6% organic matter. So humus, let's talk a little bit about humus. It's not hummus, the dip. This is a form of stable organic material. And it is the final stage, the final and most stable form of organic matter in the soil. So it's kind of the end stage of all of that biotic decomposition. And it is the main component of what makes soils dark and rich and productive. And it also contributes to soil structure, soil condition, and cation exchange capacity. So it improves overall functions of soil. And so now that takes us into cation exchange capacity. And cation exchange capacity and pH are interconnected. They're closely connected and interact with each other. They play a kind of a critical role here as far as soil health and how soil functions. Clay particles and organic matter provide the majority of exchange sites, and these sites are negatively charged. So soil nutrients exist in the form of positively charged ions known as cations and negatively charged ions, and those are called anions. And so these cations and anions are what we know of as our macro and micronutrients, such as phosphorus, nitrogen, potassium, the macros. And these are all being exchanged between these exchange sites in the soil for either hydrogen or hydroxides. In the soil, I won't get too too into the weeds, so to speak, no pun intended. But generally what we need to know is that clay particles are negatively charged, and as are organic material particles. And so that is where this exchange interface happens. And the cations absorb to the negative sites on clay particles. And we have a diagram here that we can kind of visualize. So a soil's capacity to hold these cations is called the cation exchange capacity, or CEC. And to further illustrate the chemistry here, the soils with a CEC of 1, so that's just a standard measurement of CEC, but that equals 6 quintillion, or 10 to the 18th exchange sites. So that's a lot of zeros behind it. That's how many of these negatively charged exchange sites exist in 100 grams of soil. So it's quite an extensive chemical kind of operation happening in the soil. So CEC is important. Why would CEC be important? Because that's going to define and kind of control how the nutrient holding capacity of soils. So how available are nutrients to the roots of plants. And so a low CEC soil will be able to store less nutrients because it doesn't have anywhere to hold on to in the soil. So these clay particles or organic matter. So a sandy soil with not much organic matter or exchange sites is going to suffer from leaching. It's going to be low nutrient, not able to hold on, not a very rich soil, so not high in fertility. And so CEC, as I mentioned, is closely connected and interplays with pH. And the kind of simplest explanation of pH is that it refers to the acidity or alkalinity of a soil. So for example, a pH of 0.7, which is right in the middle of our pH scale, is neutral. So that's going to be something that is not acidic or alkaline. And pure water is the standard, is the definition of neutral pH. And anything above 7 pH will be alkaline or sweet, or also known as basic, because if you taste the soil, it has a bit of a sweet kind of taste. Now, in contrast, the soil with a pH of 6.9 or lower would be categorized as acidic or sour. And the measure of alkalinity, again, is the measure of acidity or alkalinity, but more specifically, it's the measure of hydrogen ions on soil particles and in the soil solution. In the same kind of definition there, it's also, so if we have higher concentration of hydrogen, free hydrogen ions, we have a acidic soil. Whereas if we have more hydroxide ions with those negative charges, we have a more alkaline soil. So this also ties back into CEC. So generally, if you have a higher CEC, you have a higher pH. And that's going to mean that you have more exchange sites for positively charged particles. And so kind of something to note here about pH is that it's a logarithmic scale. And so what that means is that each whole pH value below 7 is 10 times more acidic than the next higher value. So to put that into an example, an acidic pH of 4 is 10 times more acidic than a pH of 5, and 100 times more acidic than a pH of 6. So every time you go up, you times it by 10. And so what this means is that it's much harder to lower pH than it is to raise pH. So if we have an alkaline soil, it's going to be more difficult to lower it than if we had an acidic soil. It's a bit easier to raise that pH. But the most important thing to understand here is that most Illinois soils are within the range of kind of 6 to maybe 7.5, and most of our horticultural plants prefer somewhere between 6 and 7. And pH has a huge influence on nutrient availability. So the degree of acidity or alkalinity of a soil will determine whether nutrients can be absorbed by plants from the soil. So as an example, a soil that has become increasingly acidic, that's in the range of 5, somewhere in there, the nutrients the macronutrients like phosphorus, potassium, and other micronutrients become tightly bound to the soil. So they're held on very strongly to those exchange sites and can't be absorbed by plants and things such as this. So we can kind of see here in this availability range, it makes sense that plants typically like the range from 6 to 7 in here, because that's where almost all of the critical plant nutrients are available. So it kind of works out perfectly that way. Whereas if we get down into these lower pHs, things lock up and become more unavailable. And so here is a closer look at what's happening within that soil solution. So the total number of cations a soil can hold is the soil CEC, and a higher CEC value. So a good CEC value is 20, somewhere around there, or even 30. And this number is the milliequivalents per 100 grams of soil. And that's really doesn't mean a whole lot for just general gardening, but that's what that measurement means. And it indicates a higher negative charge and a greater capacity of that soil to hold onto cations. Now on the lower end of CEC, that's about 4 or 5, and that's where we're looking at a very nutrient poor soil, not a lot of organic matter, a sharp draining, probably higher sand percentage in that soil. And it can't hold on to nutrients for very long. There's nowhere for them to anchor or connect. And the important take home here is that at lower pH, there are typically less exchange sites. So, oops. And there are more exchange sites at higher pH. That's really what is important to take away from this. And what this is showing, these are our cations exchanging in the soil solution between our root hairs and our clay particles. So how do we raise or lower soil pH? So just in practical terms, these are just recommendations. They're not guidelines. They're just examples to get a more accurate or precise amount that you might need, just as a service announcement, is to use a soil test. And we'll also talk about soil tests here shortly. So generally, to lower pH, we're going to be looking at applying elemental sulfur. It's also called potash. Sphagnum peat moss is an organic material that can also lower pH, or we can also use granular sulfur and mix that into our topsoil. And this recommendation is for 2 pounds for every 100 feet every 3 months in concert with testing. So we'd be doing biannual testing along with this to see if we're getting close to the lower pH that we're looking for. To raise pH, we're going to be looking at products, lime products generally, and these come in pulverized, granular, pelletized, or hydrated forms. You can also use wood ash as a way to lower your pH. So to make it more acidic, if we're up at a higher pH in the 8 range, we're going to be using things like, let me revise that. So we're looking at raising pH if we're in the acidic range. So rather than higher, if we're in the lower range, say we're in the 6s, somewhere in there, we're looking at applying lime. And at 8 to 10 pounds per 100 feet every 4 to 5 months, and doing our testing to gauge where we're at. And again, I mentioned soil testing, and Katie had talked about soil testing in our first class. And this is a nice soil test with bar graphs and easy to read here. So this has some really important information for our soils. And here we see we've got our soil pH 7.3. That's in an acceptable range. It shows us our nitrates. Maybe that's in a little bit of a high range there. So I will be returning to this for the plant nutrient class that we'll be covering next week, next Thursday. So I'm not going to spend a ton of time here right now on this, but just so you have an idea of what your soil tests will look like and what important information this is telling us. So it's also telling us here that we have a low percentage of free hydrogen ions. So this is a pretty good CEC, but it also kind of could indicate that it's a more sandy soil. So let's look at our organic matter. We're deficient, and that kind of goes along with the CEC and the pH. So this soil sample, basically, the analysis tells us that we need to increase our organic matter. We're kind of low in organic matter. We could maybe increase our potassium here and zinc, So this is great. This kind of shows us in graphical, easy to see ways what our nutrient levels here are. And from there, we can come up with a fertilizer schedule or some recommendations. And something to note, this example is from California. So that could explain some things about the soil sample, why it's got lower organic matter. I would suspect it's maybe a drier, sandier soil. And we will return to this on the plant nutrient class. But clay and silt soils generally have between 15 and 25 CEC in Illinois. And CEC can go up to 100 in what would be called muck soils. If we're looking at very swampy, mucky soil that has other issues. So it can go up to high ranges. Kind of something to talk about here. We'll talk about how to address excessively dry or wet soil. So this graph is showing us infiltration rates of different soil textures. So sand is going to drain, a lot more sharply and rapidly than our clay soil. So on this kind of spectrum from clay to sand, the problem here is clay soils are slow to absorb water, but once they do, they hold on to it for a long time. And that becomes the issue. That's the problem there, is that they're not releasing that water and creating anaerobic conditions around soil roots and soil organisms. which soil organisms and the roots of plants need oxygen. So as we kind of move down the spectrum here, we start to see whereas sand is rapidly draining out, and within 6 hours, it's infiltrated a lot more deeply into the soil profile. So we want a combination, somewhere in the middle here. This loam is where we have a good mixture of water holding capacity and drainage, which is what we're going for with our soils. And a way of determining soil moisture is to do a soil moisture field test or a finger test. And I am not going to spend a lot of time on this because it's kind of a longer involved topic here. But generally, we're rolling soil into a ribbon and then kind of pushing it out through our fingers. And the easier it breaks up and breaks off into clumps can start to tell us how much sand or silt we have. Whereas if we're getting these long ribbons, that tells us we've got higher clay percentage. And there's also soil moisture meters that we can use as well. But this method is pretty easy to learn. And this is a link to a more in-depth explanation of this practice. And technical difficulty there, but here we go. This is where that link will take you to the USDA approved instructions there. So I would encourage you to take a look at that. Okay, got a few more slides here, and we're just going to talk about some ways to manage dry soil, manage wet soil, and generally keep our soils healthy. So nutrients are less available in dry soils, water is less available, and they tend to get hotter quicker, which stresses plants out. Ways to manage dry soil are one kind of logical way would be through irrigation. But again, a dry soil, you know, we're going to be running into, if it's a sandy soil, running into leaching of nutrients. And if it's a dry clay soil, we're having issues with, now we've got a waterlogged soil. So we've traded one problem for another. Exceeding its filtration rate is going to be something we'll have to keep an eye on with irrigation. So we can kind of help these drier soils by mulching and composting. So a layer of mulch or compost is going to help that soil retain water a lot longer, and over time, that organic matter will start to integrate into that soil and improve the water holding capacity and drainage and porosity of the soil. So that's where we're adding, not only adding organic matter, compost, but then also mulching on top. We could also try windbreaks to try to mitigate some evapotranspiration from wind, and using reduced or no-till gardening practices. So the other side of this, managing wet soils. So wet soils are a problem because, again, we have these anaerobic conditions, poor aeration, poor nutrient uptake, poor root growth, and it encourages all kinds of diseases, fungal diseases. So ways to mitigate or improve these kind of soils is through plant selection. So if we're using some methods here, such as incorporating organic matter to improve the soil, maybe diverting water to a rain garden, and using, even altering the landscape, there still may be features about that soil or that site that it may just be close to a water table in some cases. So we may have to look at planting crops that are more adapted to wetter conditions, such as greens, brassicas, or even tropical taro root or something along those lines. So in order to change a wet soil, sometimes it takes some drastic measures where we're really changing the the topography, bringing in backfill, and diverting water. So changing soil texture is something that you can do, but it is something that comes with risk. So it's an extreme measure. We can sometimes modify soil texture by adding in amounts of sand and organic matter, or if it's a clay soil, adding sand and gypsum. But it needs to be done in a very judicious way, because if it's the wrong, if it's the inappropriate mixture of sand, you can create concrete where these clay particles fill in even tighter around sand particles and create, I mean, by all definitions, concrete. But if we use the right percentage, if we kind of go past that point of where that reaction occurs, you can modify a clay soil. However, it takes a lot of sand, and by doing that, you've created an environment that's going to be tough for a lot of the desirable plants. When you do that, you've created now more of a rain garden that's going to be more conducive to prairie type plants. So it depends on what the goals are here. And again, with wet soil is definitely reduced or no till, because tilling wet soil is very bad for the existing soil structure. Okay, so kind of wrapping up here, let's take a look at the Natural Resources Conservation Service Web Soil Survey. And this is a really awesome online free resource by the Natural Resource Conservation Service. And it's a tool that we could use to find out what our soil type is on our sites. And there are thousands of unique soil types from these soil surveys. And so we'll start a new session here. So I'd just like to quickly demonstrate how to use this resource. So we're going to go over the quickest way that I use it is I'm just going to type in the extension office address, come down here. We're in Illinois. Jackson County, and then we're going to view, see where that gets us. So now if I go to zoom in, so I want to get just a picture of my office. And sometimes it takes a little bit of kind of, whoops, now it took me, not sure where we are now. So I'll have to zoom out here. I think we're pretty close. So that looks like 13. So just bear with me here. It takes a little bit of navigation. Okay, so there's Ava Road. And that's where I wanted to get to. So it just takes a little bit of maneuvering. You can kind of switch back and forth. This hand helps you kind of move around the screen. But this is where I wanted to get. So now I'm going to create an area of interest. So my area of interest, I want to know what the soil type is at the kind of the back acre of, or the back couple acres of our grounds at the office. So I've created my area of interest. Now if I go over to the soil map, that's going to generate what we have from the soil survey. And I look over here, and this is telling me that 437B is red bud silt loam. And we've also got 434B2, and this is ridgeway silt loam, and that's the highest percentage of in that acreage. And this is a 2 to 5% slope. So if I click on that soil type, it's going to open this up and give me further information, such as precipitation, weather information. It'll tell me the profile here in the top in that topsoil. We have silt loam. In the horizon 2 subsoil, we get into some silty clay loam, and then stratified loamy sand to sandy loam, and even further properties and details. Down here, it says it's well drained, which, you know, in some of it maybe it is, but some of it I can tell you it's not so well drained. But this gives us a baseline of information about what is out here, and that can further inform what we can do with that soil. So this is a great resource to play around with. You can find out what soil is surveyed for your home garden, your home landscape. And I do have just a couple resources here. So the soil testing service that we use at the Jackson County Extension is Southern Illinois Ag Solutions for soil testing, and they're local here in Carterville, I believe. And they have a pretty standard soil testing program and analysis that's pretty easy to understand. For a more analytical, kind of more sciencey, more detailed in analysis, I use Brookside Labs, and there's the website for that. So that, I think, is our last slide, and that pretty much wraps up the basics of soils. It's a lot to cover, and it's difficult to touch on everything. A lot of it we have to gloss over with the time, because it's such a huge and complex kind of topic, and there's so much going on with soil. So I hope that this has been informative, and we have time to answer any questions.
Okay. Yes, we did have a few. Thank you, Austin. That went really well. Okay. Do high clay content soils automatically have a higher CEC?
Generally, the CEC, so a high clay soil is going to have a lot of clay particles, and so that generally means that it's going to have a higher percentage of exchange sites. And it's not always the case, but generally, the question is if a high clay soil is going to have a high CEC. Is that right?
Yes.
Yeah, but generally, and that's also going to mean you're probably going to have a higher pH. So the two kind of are kind of in combination. So they move together.
Okay. Okay. We had another question, and I kind of answered this one, but they were asking, they had a soil test done, and it wasn't as easy to read as the one that you had showed.
Right.
I suggested them to always make sure you contact your local extension office, because someone there, they can get you with someone that can read it. But also, I know you had mentioned the Ag Solutions. I guess it would just be getting a hold of your local extension office to see what soil testing you have available.
Right.
Okay.
That was a graphical soil test, and the soil tests that we use are pretty basic, but they have the important information, and they have recommendations. So I would definitely recommend them to talk to me or Katie or even Talon Becker with a soil analysis, so that we can help you with recommendations, because those sometimes the soil tests are more geared towards agronomic crops and field crops. So the amounts and the recommended forms of these products are going to be in larger amounts than what you would use for kind of the garden, the home garden setting. And real quick, I did want to go back to the clay question. It does depend on kind of the fertilizers that are being used. If you're using a lot of nitrogen fertilizer in a clay soil, that's going to cause it to be more acidic. But I think by kind of the general kind of guideline would be that yes, they are kind of coexisting. The pH, as pH goes up, CEC goes up, and that is usually due to higher organic matter and clay content.
Okay. We have a question about the soil survey, the mapping. How I think it's more how often is it updated? They asked if it was live, but I knew from that picture it wasn't because there were a lot of cars in the parking lot.
Right. It's not real time. So those soil surveys, that's a good question. It's every couple years. That one is probably from a couple years ago. It's that soil website is really interesting because you can actually go in and look at historical soil surveys over the last 100 years, and you can find aerial historical photos in there too, which is really interesting to look at. But as far as how recent it is, I don't know for sure. It's not brand new, I can say that. However, unless things have undergone new construction development, or they've been modified recently through agriculture, then you can pretty much know generally that it's still going to be generally that soil type. It takes a long time for those soil types to change.
Okay. Does soil testing address other concerns like fungus?
Well, in some ways it does, but that's in the organic matter part of it. So you kind of have to read between the lines there and sort of critically analyze those things. So organic matter, that's going to be, again, that biotic portion. So if you have high organic matter, you can expect there to be higher fungal activity, beneficial or harmful fungal activity, hopefully more beneficial. But that organic matter reading is what is going to tell you generally what you could expect with that kind of fungal mycelial activity in the soil. And there are things that you can apply beneficial fungi to your soil that is going to be help to establish healthier plants and roots. That there's products out there, powders and wettable powders to apply to your soil to mix in. And that's something I didn't really talk about too much that I might talk about with plant nutrients is all plants associate with some kind of fungal organism. So, however, with those kinds of soil tests, it doesn't, at least I don't think most of them specifically take a reading on fungal activity. That's going to be pretty much wrapped into the organic matter.
Okay. I have one more question. To lower pH, is potash the same as potassium sulfate? Do you use a different formula to lower pH than elemental sulfur?
Yes, potash is synonymous with sulfur. So I think it's just a different name for the same form. Let's kind of go back and look at that if I can here. So elemental sulfur or potassium sulfate is, as far as I know, it's pretty much synonymous with potash. So
Okay.
you'd use it the same way to lower pH.
Okay. I think that's all the questions we have. I did want to announce that I will be sending out an evaluation, and I have the link to the web soil survey on that email in case you would like to check that out. And I just want to say thank you, Austin.
Thank you.
All right.